Hello everyone, this is Julie Ellingson, the Laboratory Director here in Fort Collins, Colorado. For ALS, we are the RAD Lab, and I'm going to talk to you today about radium analysis and which method you might want to choose. So just to give a quick start. The radium is a natural occurring element that has approximately 34 isotopes, and all of them are radioactive. The longest living isotope is radium-226, which has a half-life of 1,600 years, so it's not going anywhere. After that, we get down to radium-228, which has a half-life of 5.75 years. So those are the main two isotopes of radium that people are going to be looking for. After that, the other isotopes have half-lives measured in days down to seconds, and so most of the time they're not a concern. Radium comes from 3 different decay series. We have our uranium decay chain, which starts with uranium, and as you can see, that's where radium-226 it comes into play. It decays into radon-222 and then further on down into some lead and bismuth, which become important when we start talking about some of the methods that we'll be looking at and how we'll analyze for radium-226. We have an actinium decay chain, which has radium-223 in it. Radium-223 has an 11.4 day half-life, so it comes into play usually as a problem more than an actual analyte of interest. The thorium decay chain is where we're looking at usually radium-228. This is also where radium-224 is, so which we'll talk about that a couple of times. Now, radium was once used very commonly. Wristwatches, the little old glow-in-the-dark dials, that was from radium, and it was put into toothpaste, and it was thought to have curative properties, and people were encouraged to consume things that had radium in it. Nowadays we know that's a very severe health effects that radium can have, and would never advise any of that, and it becomes a concern for environmental testing. And there's a number of ways to test for radium. And we're going to talk to you about some of the different methods that are out there so you can try to find the right approach for the project you are doing. The first one we're going to talk about is radium-226 by Gamma Spectroscopy. So it's the 901.1 method, and we're going to use the lead and bismuth ingrowth. So this goes back to that first decay chain where I said radium-226 decayed into radon gas. That's how this is working. We're going to take it and seal the product into a steel can and allow that radon to ingrowth, so that gas to build up in the can and then decay into the lead and bismuth, count the lead and bismuth, and be able to report the radium from there. So this is a good method for soils. It's fairly inexpensive. The detection limits can get down fairly low. I have 0.5 listed here, but we have done some projects that we all gone all the way down to 0.1 picocurie per gram. You do need a number of volume for it. 250 mils to 300 is usually what we advise for grams. It does require an ingrowth period, though, to get that radon gas build up in there. So the method states 21 days of ingrowth. So that means your turnaround time usually leads to 30 to 45 days depending on the size of the project you have. You can get shorter ingrowth and count the sample with less than 21-day ingrowths, but in doing so there's a possibility of having a low bias because you are not getting your progeny up there and for the calculation to be as accurate. You can also run radium-226 by Gamma Spec by using a direct count. So in radium-226 has a gamma line that has an emission of 186.1 keV. but you're going to get an interferent from uranium-235. So if you have uranium in your sample, you're going to have, on that peak, we cannot differentiate between radium-226 and the uranium-235. So it's possible to have a high bias. You're going to get a fast turnaround on this. You can get okay detection limits, pretty low on soils, a bit higher on waters, but it is for a high bias on here. This is a good approach, though, if you are going for a waste sample and you're just needing to know, I need to be below this limit for the landfill, because as long as we get a result and it's below that limit, even if it's biased high, it should work for your project. Now we get into a little bit more direct radium analysis. So radium-226 by gas flow proportional counter, which is going to have methods 903.0 or SW9315 are the two common references for this method. It was designed to provide total alpha emitting radium on waters. It's a screening method. So you're doing a precipitation and you're getting all the alpha emitting radiums in this digestion method. In order to report just the 226, you're kind of allowing usually at least a 14-day waiting period, because you're going to get all of your radiums in this. So you're going to get radium-223, which has an 11.4 half-life, radium-224, which has a 3.6-day half-life. So in order to get just, if you want to have this reported as radium-226, you do have to let some time go by and have some ingrowth. It's really best for waters. You can use it on a soil, but the chemical separation has a lot of interferences when we get into soils, and you will end up with a higher detection limit. It can be fast, inexpensive. You get detection limits of at least 1 picocurie per liter, possibly lower. But like I said, it is going to have a potential high bias for the 226 if you have any of the other alpha emitting radiums there. So radium-223, radium-224, you can eliminate that, or not necessarily eliminate it, but at least reduce it with a decay period of 14 days. So that's going to extend your turnaround time on how fast you can get this done. Radium-226 by radon emanation. So this is EPA method 903.1. There's also a standardized method for it too. This is developed for waters, has been modified to be used for soils. It again is a co-precipitation of barium to separate out the radium, and then we ingrowth it. We're using the radon progeny as a gas and transferring it and counting that. It's really no known interferences for the 226. You're not going to have a problem with the radium-223 or the 224 interfering with this, because we're going actually off the radon gas, which is a direct product of the radium-226. You can get low detection limits on this. It's a little bit more expensive just because it's a little bit more involved on some of the transfer process, but you can get a potential faster turnaround time. The ingrowth period is not 21 days like you have for gamma. We don't have the 14-day decay period that you need for the gas flow proportional method, but you still do need some time to ingrow that radon gas in there. So we have at least 4 days. The longer your ingrowth period is, the shorter or the lower the detection limit you can get is. Soils can be a bit problematic for this, even though we have modified the method to be able to do soils in there. The key to this is getting a thorough dissolution on the soil to make sure you get everything in there. So in order to do that, we actually do an HF digestion for it to ensure that we're getting a total dissolution of the soils. We can also run radium-226 by alpha spectroscopy. This method was developed to do really low level measurements. Very complex digestion and chemical separation that we're doing to get there. So it can be done quickly because there's no ingrowth or decay period needing. And in fact, if we count the sample within, prep and count it within 3.5 days of collection, we can actually report the radium-224 fairly accurately. This is a fairly expensive. It is meant to be used in very low-level determinations. So, and in cases where you might actually need the radium-224. We developed this method twofold. Part of it was originally done when we were working with Homeland Security on a rapid method for 226, and we've further on have refined it with the USGS for a lot of the stuff that they're doing. Now we'll get to radium-228 and the methods we can use for that. So first one we're going to talk about is radium-228 by gas flow proportional. So EPA method 904 or 9020. This method was developed for, again, for waters. In fact, actually, most of your rad methods were developed for waters. We have adapted it to accommodate soils. It's really still better for waters. Again, this is a co-precipitation, leads and bariums to refine it and get down, and we're going to allow for an ingrowth of actinium. On the instrument and everything, that is actually what you're going to be counting is the actinium-228, which again goes back to the decay chain where you have the radium-228 going into actinium-228. So that's how we get to there. Again, in solids, you have to digest this and get it transferred over into a liquid base and then pretty much run it through how you would a liquid. So you're going to get a bit more interferences again from dealing with soils. It has a involved prep, which can prevent a quick turn depending on the number of samples that you're trying to get done at a time frame, but it's fairly moderate in price. Detection limits typically are about 1 picocurie per liter in waters and 5 in soils. Again, the soils are a bit higher due to the interferences that can be in the soil matrix with the digestion. You can also run radium-228 by gamma, the 901.1 method. This is a direct method measurement of the radium-228 using the actinium. So again, both methods, you're counting the same thing. They're both counting actinium. Reasonably inexpensive. You get good low detection limits on soils, not as low in waters. Volumes needed range from 125 grams to 550 grams. 1 liter for waters, or if you're doing a waste liquid, a little bit less. This is something that you can actually run in conjunction, so with the radium-226. So if you're running Gamma Spec, you can actually count for radium-226 and count for radium-228 in the same analysis. So a quick summary of the different methods we talked about here. We've got, again, your 226 by gamma, really good for soils. It's going to have a long turnaround time if you need to have the full ingrowth on it. It's fairly low cost. Your radium-226 by direct emission, you can do a fast turnaround time. Again, it's a low cost, but you have to remember that there's a possible high bias when you're running it this way. Radium-226 by gas flow, it's good for waters, not so much for soils. It really was meant for a screening method for 226. It's total alpha emitting radium is the actual name of the method. It'll be a longer turnaround time if you need to try to isolate the 226 as you're going to want to decay away everything. Again, fairly low cost. Your radium-226 by the 903.1, your emanation, it's definitive for 226. Good for both waters and soils. You can get a faster turnaround time, and it's a reasonable cost, a little bit more than your 903.0, but not bad. Radium-226 by alpha spectroscopy is meant for low-level samples. This is when you're trying to get down to less than, 0.1 picocurie per liter. Overall, we do it more for waters than we would for soils. You're possible to get the radium-224. So if you need a number for radium-224, you can do that. Now, in some cases, other people have gone and you can get a radium-224 estimation by running it by gas flow, where you count the sample right away, let it sit for 14 days, recount it, and mathematically say, well, this is what my first count was, this is what my second count was, so second count is my 226 number, and the difference to get to the first count, that's what 224 contribution is. So it is an estimation of just making assumptions that you don't have any 223 in there. Now the radium-228 you can run by gas flow, and it's good for waters, not really best for soils. You're going to get a little higher detection limit, fairly reasonable cost. 228 by gamma is good for soils. Again, you're going to get higher detection limits for waters. It's going to be your low cost, fast turnaround time possible. There's no ingrowth periods needed, no decay time periods needed, so you can go with that. Now there's a couple things you should note when talking about radium analysis. You're going to see many regulations out there that are going to list something. They say, oh, I need a combined radium-226. Well, this will require two separate analysis. Radium-226 is an alpha emitter and radium-228 is a beta emitter. There's not really a way to run a test and get a single number for radium when you want both radium-226 and 228. There's also no official guidelines on how to mathematically combine the number, so you can run into slight differences on how lab A and lab B are trying to combine it, or you might have another lab that says, you know what, we'll just let you figure that part out, here's your two numbers. A request of total radium might not necessarily mean the same thing. Total alpha emitting radium a lot of times is just simply referred to as total radium. So if you ask for total radium, there's a chance all you're going to get is radium-226 with maybe the 223 and 224. So you need to be aware of what requirement you are needing to answer to. So if you're doing, say, a NIPTES testing, most likely you just need total radium, the total alpha emitting radium. But if you're sampling for a CCR regulation, you're going to need both a radium-226 and a radium-228. So it's definitely good to know what exactly you're needing and to understand that there is some nomenclature confusion on what things are. So just to go back and kind of a funny thing on the curative products of radium, used to have these radiators where they're crocks lined with radium ore, and you were to fill the water up and let it sit overnight and then consume the water the next day to have curative properties and be healthy and everything. So I've always found that kind of entertaining with nowadays with all your regulations we have that we don't want radium in our water. So at that, I'd like to again thank you for your time of listening to me and see if anybody has any questions. All right, well, I don't see any typing in, so hopefully I didn't bore you to sleep or anything, but and hopefully I gave you some information that will help you figure out what test that you might like. So And at that, again, thank you all for coming.